Okay, is it working? Good. Well, first let's state a plan. Well, the first item is multiplicative cohomology theories, and we'll briefly discuss those and how they come from spectra of a particular kind, and hopefully today we'll prove the Poincare duality theorem, and then basically we will have covered the basics of generalized homology and cohomology. Well, let's first state some simple general facts about monoidal categories. Well, first, there are such things as monoidal categories. Well, a monoidal category is a category with a sensible notion of a product. Well, I use smash to denote the product, but one could use any symbol one likes. Okay, do we need symmetry? Let me think. No, we don't, actually. Well, most monoidal categories we encounter in everyday life are symmetric, but not all of them are. In a symmetric category, in a monoidal category, one can define monoids. And there are lots of examples. Well, for example, Well, for example, the usual monoids which are sets equipped with a binary operation, which is associative, has a unit, but does not necessarily have inverses, are monoids in the symmetric monoidal category set with the Cartesian product as the monoidal structure. Well, similarly, so let me somewhat belatedly say that I use S to denote the monoidal unit. So here S is the monoidal unit. Well, similarly, to monoids, one defines comonoids. Basically, one takes the definition of a monoid and inverts all errors. And well, let's see what the comonoids in this example are. All sets are comonoids. Well, the monoidal unit in this particular case is the 1-point set, and the structure map from x to x squared is the diagonal. Very well. So, in a sense, there are more comonoids than there are monoids. They are more common. Well, let's state an observation. Suppose we have a symmetric monoidal category and a monoid and a comonoid. Then the set of maps from the comonoid to the monoid is a monoid. And similarly, the maps from a comonoid to from a monoid to a comonoid form a comonoid. We will only need the first part. No. So let me explain how the first part works. I take maps from C to M. You know, the words from the comonoid to the monoid. And suppose I have two maps, F, G from C to M. I first take the co-product for C, then take F smash G, and then take the product for M. And it's it's easy to check from the axioms of monoids and comonoids, and that this product is associative. So when I say plus axioms, these include in particular the associativity axiom. Okay. Now I have to find a product, but I also need a unit. If I just have a product, it's better than nothing, but it's not a monoid yet. I need a unit. So, how do I define the unit? You know, the words I need some preferred map from C to M. How do I define it? Yes. So C, S, M. I take the co-unit for C, compose it with the unit for M. Okay. So so we have this general categorical nonsense, which is actually despite the fact that it's general nonsense, it covers a lot of examples. For example, again, let's take the category of sets with the Cartesian product as the monoidal structure. What do we have? Well, suppose we have G a group and we very often use the following construction. We take some set and we take functions with values in some group. Well, this is a particular case of this. Why? Because G is a monoid. We know this. And any x is a comonoid, so we get this. We get this construction. In this particular case, we can say more. If G is a group, then set X G is a group. Now, the general categorical nonsense doesn't quite tell us this. Why not? Because the monoidal structure we use here is completely general. Is there a way to define group objects? So what do we need to require from a monoidal structure in order to be able to define a group object? Firstly, we need a map from the multiplication, the map from G to G, G cross G to G. We need the unit. Everything makes sense for an arbitrary monoidal structure. Now, what about the inverse? The inverse is a map from G to itself, such that if and now I want to run into problems. I can define the multiplication, which is G cross G or G smash G to G. Very well. But now I need something else. I need a map from G to G smash G, which I would then like to compose with the identity smash the inverse to state the axiom for the inverse. Now, unfortunately, I don't have, in general, a map, a sensible map from G to G cross G. But sometimes I do. When? Well, sort of. But there's a general condition on a monoidal structure which guarantees basically which generalizes this this property that every object is a comonoid. And what is a structure? Well, this is the Cartesian structure. And what's the Cartesian monoidal structure? Well, it's the monoidal structure given by A tensor B is equal to the limit of the maps from A and B to the terminal object. And well, this structure is Cartesian, and there's the standard monoidal structure on topological spaces is Cartesian, and so on. Anyhow, we sort of got distracted. Anyhow, so monoids can be defined for an arbitrary monoidal structure. Group objects, not so much. Anyhow, okay, so now we want to apply all this to yes. So we want to apply all this to the homotypic category of spectra. Okay, so ring spectrum ring spectrum is just a monoid. Now, and there are there are many examples of ring spectra. For example, basically some of the first examples of spectra are ring spectra. One particular example is the Eilenberg-MacLane spectrum of a group R, which is the additive group of a ring. For example, the Eilenberg-MacLane spectrum of Z. Now the next example is the K theory, and then there's its variants such as the real K theory and so on. Wardisms of every description, or almost, and so on. So on the other hand, the suspension spectra are usually not ring spectra. So we have monoids, but this is not all we need. We also need a comonoid. Where do we get those from? And the problem is there's no reason to expect that a random spectrum will be a comonoid with respect to the standard monoidal structure. So, what do we do? Well, it turns out that there is a class of spectra. So there is a class of spectra which do give us comonoids in whole spectra. Well, first, let's look at spaces. Well, we still have lots of time. By the way, does anyone know how to fix the clock? No. Okay. Anyhow, so to see why some spectra do give us monoids, let's have a look at spaces. So let's focus on spaces with the monoidal structure given by the smash product. To avoid unnecessary complications, let's say that we only want to consider nice spaces. Anyhow, what's the unit? So we have the monoidal structure given by the smash product. Very well, but what's the unit of this monoidal structure? No. If I smash anything with a point, I get a point. And this is not what one would expect from smashing with the unit. Yes. So the unit is the S naught. Okay. Now, okay. So every space is a comonoid, and no, not so fast. Now we again belatedly remark that we are now considering pointed spaces. Otherwise, smashing doesn't make sense. But the unit is still S naught. And now for every space, if I define x plus as x union some point at infinity, and declare this point to be the base point, I get a comonoid. Basically, the problem if I don't do this, the problem is having a map into the monoidal unit. And otherwise, if I don't do this, then how do I map x into the monoidal unit, which is S naught? Well, I can map everything into the fixed point, and this is possible, but it will give me zeros afterwards, so it's not very interesting. or I can take some components to the fixed point and some components to the other point, and it will not be. This procedure is not functorial, and so on. So I add an extra point. Okay, let me explain the structure maps. Well, let's look at this. I need a map from x plus to x plus smash x plus. But what is this thing? This is x cross x plus infinity. And this is x plus infinity. So what do? I take the diagonal map on x and the infinity will go to the infinity. Okay, so so I have to find the map from x to x by x and x plus s naught. And the map from x plus to x naught just takes everything apart from infinity to the base to the non-base point, and the infinity to the base point. Okay, so every space, even without a base point, gives me a monoid in this monoidal category. Sorry, comonoid. Very well. What do I do next? Well, next. Well, next I consider the infinity suspension functor. What does this functor do? Well, it takes everything to its suspension spectrum, and this functor is monoidal. to be honest, we need to remember that we only have the product structure on the homotypic category of spectra, so we need to be careful. But the thing is, we we have the sigma infinity functor on the level of the homotypic categories too, and then as we saw, we get something which is a monoidal functor. Now, in particular, this means that the functor is monoidal if there is an isom. Well, let's say there are several versions of what it means for a functor to be monoidal. Let's say that that in the homotypic category of spectra we have an isomorphism which is functorial in x and y. There is a way to make everything work on the level of spectra, but it's complicated. Let's not worry about it. Okay, so and let's also require that the unit should go to the unit, and this is clearly the case in our situation. Well, so. What's the point of all this? Since sigma infinity is compatible with the monoidal structure, it takes monoids to monoids and comonoids to comonoids. So every So for every space X, the suspension of X plus is a comonoid in spectra. Okay. Let me get some water. I need water to function. Water is life. Рад, привет. Okay. Well, let's open the window and then we'll close it in a few minutes. Okay, so every space gives us a comonoid, and in particular, if well, let me use X. No, X. Okay, Y. Because why not? The ring spectrum. Then the set of maps from the suspension spectrum of X plus to Y is a monoid. Well, we also have another monoidal structure on spectrum which gives us the product. And if we want this to be a ring, we need to describe how the monoidal structures are related to each other. And we basically stated, and maybe we did prove this, maybe we didn't. We have the distributivity property for the two operations. So both for spaces and for the elements of the homotopy category of spectra, we have this distributivity condition, and let's let's see what the benefits are. So again, let me formulate a general categorical observation, and then we will see how it applies to spectra. So suppose we have a monoidal cat, which well, suppose there is an initial and a final, or terminal, I should say, objects. And suppose also there are finite sums and finite products, and these are the same. What's the sum? Is the push forward? Okay, so. So the sum is the push forward of this diagram of the maps from the initial object and there's a dual definition of the product, and suppose the both exist, and suppose they are the same. What does it mean exactly that they are the same? Is there a map from the sum to the product, or from the product to the sum? Yes. So there's a map from A plus B to A cross B. How do we construct it? Well, okay, so yeah, it should be the other way around. A, B. Okay, A maps to A, and B maps to B. So, and both map into the final object. So what do we do?
So AD plus ATB is a map from A plus B to A. Yes, it is AD plus ATB, I suppose. So it was this map.
Yes. Okay. So and this map, in general, needn't be an isomorphism. So we 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 require it to be. Okay. So let's take a comonoid. So I want to see how this product operation interacts with the sum operation. Okay, so we have this this map. And similarly, we have the no. We have a similar definition for the sum of two maps. Okay, so here, to be more precise, I first take the map from C to C plus C. Do I have the diagonal map into the plus or into the product? Let's think. Yes, so I have the diagonal map always. If I define the product using this this diagram, I always have the diagonal map. Okay, now this it doesn't matter that C is a monoid or a comonoid. I have this for every C. Okay, now I know that this is an isomorphism because this is what I require it to be. Okay, now I take the now I can take the product the sum of two maps and now, well, I have a map from M to M, the identity, so from another one from M to M, the identity, So I get a map from a m plus m to m. So this map exists just again for every m. Okay, so okay, so I have two operations on the maps from C to M. What I want to show well, I want to show the distributivity property, which in general comes in two versions because the monoidal structure is not assumed symmetric, but in our case, one version would suffice. Okay, so how to prove this this property, or the other one? Well, we assume that we have this with the wedge replaced by plus. Well, okay, so let's write the diagram for both sides of this equation. So we have C wedge C. And now I need to use okay, so C plus C, then so I need to do what I take the take the map F, which G O plus H. So I end up in M, wedge M plus M, and well, then I take the sum in M. Whilst keeping the first factor constant, and then I take the product. Very well. So this is the diagram for for the left-hand side. Let's write the diagram for the right-hand side. Well, it's sort of similar, where C goes to. So this time I take first C plus C. So because I need to take the sum of the two products. Okay, then what? Then I take C so then I take the co-product on each C individually, and then I take F smash G plus F smash H, and I end up in M smash M. Okay, and then then I go to M plus M by taking the product on each M smash M, and then I take the sum. Okay. Well, the diagrams are not the same, but they sort of look similar. For example, we have the C part and the M part in both diagrams, and basically this thing can be identified with So this thing can be identified with this thing. And similarly, this thing can be identified with this thing. Very well. So the well, let's consider the C part and the M part separately. Well, let's start with the C part. I have C goes to C wedge C goes to C wedge C plus C. This is isomorphic to C wedge C plus C wedge C. And now, okay, I have a map from C to the product, C cross C, very well. C plus C, again an isomorphism, and then I take the map from the co-diagonal, sorry, the co-product on each C. So the question is, does this diagram commute? What do you think? And if it does commute, then why does it commute? Okay, I think we need to have a break. So let's stop here, and then we'll hopefully finish this after the break. So let's have a break. Are there any questions?